Good afternoon. I want to welcome you to this presentation of a solar system internet architecture study. And your presenter is Scott Burleigh, who was many years with the Jet Propulsion Laboratory at Caltech, and was actually one of the original members of the DARPA DTN studies that started this whole enterprise of interplanetary networking. And Scott was essentially, for many years, JPL's chief DTN architect, wrote tons and tons of lines of code of DTN, and was a key member of the core team at JPL that developed the ION implementation of DTN. And he's going to be providing an overview of the history of the solar system internet, walking us through the CCSDS original architecture for solar system internet. And I think that you're going to find this very enjoyable and informative. Take it away, Scott.
Thank you, Mike. Excellent introduction. I'll get started pretty much right away. This is an overview of the material I plan to cover in the next about 20 minutes, talking about the source material for some of this stuff, which is the Architecture Green Book from CCSDS. And that includes some discussion of the rationale, business case for a solar system internet and provisioning the network, accounting, which is something we haven't even started actually doing yet, and being able to charge money for transactions that happen over the network. Transitioning from the current model for space mission communications to the use of an interplanetary network, and in specifically the three stages of that transition. And then I'll touch briefly on later work, the current work on solar system internet architecture inside the architecture working group of IPNSIG. So architecture is a slippery term. We all understand architecture as it relates to buildings. What is architecture as it relates to something more abstract like a network structure? The CCSDS, the Consultative Committee for Space Data Systems, undertook, starting in 2013, to try to nail down what architecture actually meant for the sort of interplanetary networking technology that we were working on. The document for that, an informational report, which is in CCSDS terms a green book, is this document 730.1-G-1. There's a link to it here, and I'm only going to cover a very small amount of the material that's in that document, which is about 60 pages. Anyone who's interested in pursuing this, I would urge you to download that document. I think it's generally pretty readable. It's not a lot of intense math or anything like that. This document was published in July of 2014, so 8 years ago, and we've thought a few things since then, but it holds up pretty well. Most of what was in there is not obsoleted by anything that's been done since then. The purpose of that green book was to offer space agencies an idea of what interplanetary network would look like, how it build, how it work, and that it would include both the software elements of the network and the architecture, and the procedural and organizational elements of the architecture. And I will briefly touch on both. The rationale for solar system internet is one of the early elements in the document. And as I'm going through this, anything that's in this italic font here is quoted from the document. The intent, the rationale for developing this architecture document was actually to respond to a request from the Interagency Operations Advisory Group, which had described solar system internet and an operations concept. So the concept came first, and this architecture responds to that concept by fleshing out in some detail some of the ideas. Why bother to do a solar system internet? This is a question that I think to a lot of us is like, well, of course you would, but it's not necessarily obvious to everybody who's operating spaceflight missions for national space agencies. The case here is that network communications can make missions more robust, more operationally flexible. In some cases, missions would otherwise really just not be possible. And they add some redundancy, some resiliency that can enable missions to be sustained longer and produce more data. The network can conceivably be mounted by its single space agency. But what's contemplated in this architecture document is that many or all of the world's national space agencies, and ultimately commercial ventures as well, would agree to participate in this network and cross-support missions among themselves so that everybody could obtain the benefit of the scope of this large network and not have to stand everything up themselves. The idea is that the shared resources are going to benefit everybody that's sending anything into space. In order to do this, we have to have hardware out there. And how's that hardware going to get there? It is recognized in this book that computational resources for doing this stuff, ground systems and flight assets, need to be deployed in a constructive way so that the connectivity among these things can be used to knit the network together. In many cases, the capability to operate the network protocols is something that is a sort of a side job for a spacecraft whose main job is to map something or instrument some aspect of a planet or an asteroid or something like that. And the relay function is an extra thing that they do. Ultimately, it may be necessary to deploy some spacecraft that do nothing but forward data through the network. That's an expense that no national space agency has been willing to undertake. Yet, ultimately, we think that's bound to happen. There have to be things that are deep space routers. There is the potential for funding the operation of the network by charging for services. The accounting that's necessary to do that is contemplated in the architecture. The data that's needed for that can be tracked at the points of data relaying, things like the amount of bandwidth that's used, the amount of storage that's consumed, and that information can be used to satisfy interagency agreements that are negotiated, presumably to enable everybody to be treated fairly by the operation of the network. Getting into the transitioning, how do we actually get to there from here? The current model for operating space flight missions looks a little bit like this. The schematic here is here's a spacecraft, crew or instruments in the spacecraft, and these other elements are all ground elements of the same mission operated by the same space agency. So, for example, there's a mission operations center for the instruments, and there's exchange of data between the spacecraft and the mock personnel. Engineering information also will be exchanged between the spacecraft and the spacecraft mission operations center. That's responsible for the health and safety of the spacecraft itself rather than the payload missions. All of the exchange of information is conducted by means of RF communication between the spacecraft and her Earth station, which has its own engineering information that goes to its own Earth station control center, and it extracts the information from the downloaded linked frames and passes it on to the other mission operations center using terrestrial network links, all of which has been working very well for many years, very familiar structure, but of course limited. It doesn't accommodate operations such as relaying data from the surface of the far side of the moon to Earth. How do you do that in this model? It's not really easily sustained. What we're aiming for in the long term is this networked model. And here we see a more complicated structure. There are two agencies, not just one, and there are three missions involved, not just one. And the mission engineering information from this lander, some of it goes to the instrument mock and the lander mock for that mission. Some of it is relayed by means of another spacecraft to different ground stations and different Earth and spacecraft mission operations centers. And some of it is relayed again through other spacecraft to ground stations of yet another agency, so that any instruments that belong to that other agency can be monitored and controlled the same way. So there's cross support among the agencies and among the missions, even with a single agency, that enable all the data to get to all the right places without intensive management of any of the assets. To reach that stage, which is much more complex than what is currently done in flight system operations, the CCSPS solar system internet architecture contemplates 3 stages of transition, corresponding to 3 broad grades of functionality. The stages being termed mission functionality, inter-network functionality, and advanced functionality. What's recommended in this informational document is that organizations that are participating in SSI begin operations at whichever of these stages of operation they can support, but in all cases, the more advanced stages encompass all the capability of the earlier stages. So you have to have mission functionality in order to pursue inter-network functionality. The first stage of this transition, mission functionality, is really just automating the basic communication processes that are already in place, using communication software, including, in particular, the DTN networking bundle protocol and probably the Licklider transmission protocol, which in turn utilize the link layer protocols that have been sustained by solar system internet operated by CCSBS entities for many years. An example of that configuration would be here. Now, this looks very similar to the current state of the way missions are operating. What is new is just that the communication here on these solid lines is automated communication rather than intensively managed as flight missions have been for the last few decades. The operational principles here are, first of all, that the coordination and provision of the data communications is internal to the mission. We're not looking at multi-mission or multi-agency capabilities here. There may be some cross-support, but any cross-support between agencies is ad hoc, privately negotiated. It's not part of the architecture. Inter-authority cross-support of link layer services has to be configured and operated in ways that are already familiar to mission operators now, mission operation centers. But the foundation that is established here is very important. The functional procedures that are included in this just first stage of this mission functionality includes all the basic elements of standing up the network, of installing new solar system internet nodes, requesting services, publishing the contact plans that have been established by SSI service providers, issuing data from one node to another node, just in bundle terms, you're sending a bundle from one node to another, reporting on the operation state of a node, troubleshooting the network, modifying the configuration of a node that's already in operation, emergency commanding, and a facility for estimating the time a bundle will be delivered. That's a capability that, in particular, the science teams operating these instruments are extremely interested in. Stage 2, it's the same software capabilities, but the inter-networking functionality enables those protocols to operate across multiple spaceflight missions that might be managed by different national space agencies. And the capability is there. It's important to note that still at this stage, the coordination of that mission data communications exchange is manual. It's going to be challenging enough just to get the procedures in place to enable this inter-networking, to enable this exchange of information about, for example, the contact plans that control routing through the network. Automated mechanisms for doing that are deferred until stage 3, which we'll get to in a minute. Here's an example of the operation of this inter-networking functionality. Here we've got 2 authorities. They might be 2 different space agencies. They could be 2 different NASA centers. There's a spacecraft here that is exchanging information with elements of its own mission. And there's also a relay functionality that borrows the capabilities of another spacecraft operated by another mission altogether to convey that information indirectly to the Science Spacecraft Mission Operations Center and the Instrument Mission Operations Center in the same way. So that the Authority A, Mission A operations teams don't have to have direct contact with the spacecraft at all times. The network conveys the data indirectly when direct communication isn't possible. In order to make that work, you need coordination among these authorities. And this coordination function is shown here. The idea being that you've got authority A, authority B. Authority B owns the relay spacecraft and the Earth Station Control Center. They communicate among themselves in the context of a coordination function that might include and ultimately would include additional authorities. So none of this stuff is simply asserted on one side. There has to be coordination and negotiation agreement to enable any of this data to flow smoothly and automatically. The operational principles at this stage are, first of all, a provider node can support a mission that belongs to a different authority. Interagency cross-support is explicitly supported within the architecture, not merely tolerated as an ad hoc kind of expedient. Provider nodes are potentially under different authorities. The coordination of mission data communications is still not automated, and there is a coordinating function responsible for ensuring the member authorities can negotiate successfully to enable operation of the network. The functional procedures, most of the key functional procedures are already in place. They're established in stage one when the capabilities of the mission were automated using automated protocols. What's additional at this stage is requesting cross-support in a documented and informed way, and in publishing composite contact plans. That is, in the first stage, there were provider contact plans issued by service providers. Here, the providers' contact plans are negotiated or exchanged here between authorities and coordinated in this coordination function. So what comes back is the composite contact plan that enables cross-mission operations to proceed successfully. And then we get to stage 3, which is advanced functionality, which automates the coordination of mission data communications. Nobody knows yet what that looks like exactly. There's a recognition that a lot of this coordination can be automated. It can be supported by, for example, artificial intelligence, machine learning. The details of that are far enough in the future that they have to be recognized in this document, but not spelled out in detail. And they're not spelled out in detail. The only additional operational principle here is that the coordination of mission data communications is an automated process. And there are some additional functional procedures identified at this stage of transition. Security becomes a big deal and becomes formally supported. So the distribution of security keys and the revocation security keys is part of the functionality, and detecting problems in the network and remedying those network problems in a standard network-wide way rather than on a case-by-case mission-specific basis. That's what's drawn up in the Solar System Internet Architecture Green Book. Since then, in the ensuing 8 years, we've thought some more about the architecture of the solar system. And when the IPNSIG established an architecture and governance working group in September of last year, the charter of that working group was exactly to explore those properties, beginning with the CCSDS SSI architecture concept and extending it with more detail and possibly lessons learned from experience over the last 8 years. There was a recognition that the solar system internet could be made up of multiple independent interconnected networks, and that entails establishing governance practices that can support that level of multi-party complexity. As one of the major initial activities of this AWG workshop, there will be a workshop held later this month on DTN routing. The intent here is to take a step toward being able to recommend governance practices based on understanding of what needs to be governed, in particular things like how are nodes named and how are they addressed? How is data going to be moved through the network, and how do we establish the agencies that will register and certify the entities that are undertaking that communication? So there will be a 4-day workshop later this month to look at that. And I would point out that one aspect of that challenge is agreeing on the syntax of node identifiers for the network. This is currently an active topic of discussion in the IETF DTN working group. that's all I've got to report on right now. The bottom line, I think, is that the IPNSIG believes the solar system internet architecture is generally well understood in the general sense. We've had a pretty good idea of what the architecture will be for the last 8 years. The specifics are, in some cases, still kind of fuzzy, and we're trying to nail those things down now. And with that, I will turn it back to Mike for question and answer.
Okay, thanks, Scott. So we did get a couple of questions. Jorge Amodio asked, are there any private or commercial entities participating on CCSDS? And I sent him the link. If you go to public.ccsds.org, they actually have a tab for looking at the different classifications of participants. And there are a number of associates and liaison organizations that are not space agencies. And then we have more questions arriving. So an anonymous attendee asks, what is the future of deep space routing or deep space routers? What is the future of progressing deep space routing in your view, Scott? Do we essentially piggyback existing infrastructure, or is it requiring significant deployment of new infrastructure?
Good question. Initially, nobody has got billions of dollars to build this network, right? It's not like anybody has said, here, take $10 billion and build an interplanetary network. We have to work with the materials that we've got available, in particular, the space communication assets that are available. And those assets are the spacecraft for flight missions whose purpose is science investigation. So the intent is that in the near term, in I would say 5 to 8 years, everything that is accomplished by the solar system internet in terms of routing, relaying data automatically through the network will be at the discretion of the spacecraft that are supporting these other missions. In cases where the prime mission of the spacecraft is to do X, well, it's going to do that. It's going to do X. It's not going to be relaying data through the network. But there's enough resources on most of these new spacecraft that isn't necessarily required every minute in order for it to do its main job, that we think we can deploy those resources to support network communications at the same time that the spacecraft's main mission is being sustained. Ultimately, as the scope of the solar system internet grows, I think there will need to be spacecraft that are dedicated to relay. And just exactly what that means, what are they going to look like, how big are they going to be, what kind of capabilities they're going to have, is still not at all well established. There's been talks for, I think, maybe 7 or 8 years about having a Mars relay satellite. It's an idea that we think is ultimately going to have to happen. The budget for that has not been available, and maybe it will be sometime over the next decade, but nobody's proposing that mission yet.
Okay. Ben Scott asks, hello, Scott. With regards to security, do you envisage aspects of security and threat modeling in this domain to be incorporated more formally into threat modeling? For example, the MITRE attack framework, BPSec, DTKA, etc.
I would say that securing all of this communication is absolutely necessary and is going to be certainly part of the detailed design of network capability deployments throughout the SSI. At this time, I don't think anybody is looking at threat models being part of the architecture. Rather, we think that the architecture absolutely needs to be able to support the operation, particularly of IPsec and key distribution to enable IPsec to function correctly. I think that those security aspects are, in a sense, an architecture of their own that needs to be superimposed on the physical architecture of connectivity and cross support. That may change. I can imagine the architecture working group taking up security as one of the governance elements that the AWG needs to come to some sort of recommendation on. But we're not at that stage at this point.
Okay. And then a question from Oscar Garcia. In what stage is the coordination between agencies in terms of operation?
The reality is that the agencies cooperate and interoperate and cross-support to a considerable extent now. The big difference in making the transition to the interplanetary internet is in the automation of a lot of that coordination, which currently still has to be quite heavily managed. The more we can automate that activity, the less it costs and the more affordable it becomes for all the agencies, and the more of it they can do, and the more powerful the network is. So the introduction of further automation really is the key to enabling the agency coordination and mutual cooperation sort of there to really come into fuller flow and support much more powerful communication among spacecraft that are exploring the solar system.
Thanks. Event Surf has what looks to be more a comment than a question. Scott, we will need new ground station capability to terminate bundle protocol at the ground stations for relay to NOx and potentially science teams.
I completely agree. The placement of the nodes of the network is, I'm sure, going to evolve over time. Initially, the DTN technology is new enough and complex enough that space agencies, I think, are going to feel comfortable about deploying it only in a single place, like in the center of operation of the DSN first, and being able to watch it carefully, get an understanding of how it works, get an understanding of failure modes and what they need to do to recover from them. I think as the agencies get more comfortable with the technology, the job of migrating that technology out to the ground stations, out to the ground support centers, is going to seem less daunting and will be more affordable. And it'll be important to do that because, in particular, things like impedance matching, in a sense, matching the data rate of downlink from spacecraft to the rate the data can flow over the internet is a big problem. It can be managed by manual buffering at the ground stations because the spacecraft actually, in many cases, are able to transmit data much faster than the internet can carry it away. What DTN will do is the bundle protocol will enable that rate matching to be performed automatically so that the management of that activity becomes much less of a problem. It's a huge advantage to the operation of the ground systems. It's definitely the case that ultimately the solar system internet is going to depend on the improved capabilities of the ground stations that come from installing DTN technology there. It's still, I think, a couple of years off.
Okay. And a question from Christopher Lowe. Thanks for the great summary of where the SSI is at. Question. Actually, I was going to ask this question also. Will the outputs from the AWG workshop on DTN routing be disseminated to the community, and if so, in what format?
That's a really good question. The intent of the workshop is really to enable the AWG to understand the issues and come to consensus on what they would recommend. And then that recommendation really is intended for distribution mainly to IOAG, to the space agencies, to mission operators. But there isn't anything like secret or confidential about any of this. I think the findings of the workshop, it would make all kinds of sense to make those public to the IPNC membership. If it were deemed newsworthy, I don't see any reason why we wouldn't make it available to news media as well. But it's not clear that anybody in media is going to care that much about it. But there's no reason to keep this stuff secret from anybody, sure.
Okay, and one from Quadri Adebawale. Hope I got that name correct. Many thanks to Scott for the wonderful lecture. Would the interregional routing / forwarding be built on contact graph routing, or is a new technology?
Oh, well, this is still very much under discussion. And in fact, I think that it'll come up once or twice during the workshop. There's a prototype for interregional forwarding built into a feature branch of the ION software. And that prototype supports regions that use contact graph routing internally to accomplish intra-regional forwarding, and then the interregional forwarding is accomplished by passageway nodes that are concurrently members of two or more regions. That is, they have feet in multiple contact plans. The interregional forwarding concept doesn't require that the regions that are being connected use contact graph routing internally. There can easily be some regions that use CGR and some regions that maybe are entirely opportunistic. And there are a number of possibilities. There are a number of ideas for potential improvements to contact graph routing as well. There's things that are routing mechanisms based on contact plans that can use contact plans in a way that gives higher router performance. So there is no firm answer yet on exactly what the end routing fabric in the solar system internet is going to be. Is it going to be one CGR-based region after another, or is there going to be some sort of mix? The architecture needs to be able to support both models, and I think the architecture certainly does, and I think the interregional forwarding and design also will, although right now it's more limited.
Okay. And another comment from Vinsurf. The Artemis mission already includes private and public sector assets that will need to interwork with and depend on BP relay capability, circa lunar surface and orbiters, as well as transit to Earth.
Yeah, absolutely. And the architecture definitely supports that. I would say that the software we've got available, software that's running on the International Space Station now, also would support that. What's needed is the administrative procedures and agreements, the human interactions that are going to be required to make that stuff all work. And people have to get comfortable with the idea of other agencies having access to some of their data. You can gate that somewhat by encrypting data that you don't want to expose to anybody else. But the encryption, it requires establishment of the sort of security architecture that we were talking about a minute ago, and the distribution of security keys to sustain that. There are procedural elements that are going to have to be in place to make the Artemis LunaNet work. And I think the deliberations of the AWG may help accelerate the establishment of those procedures.
Okay, a question from Eric Johnson. Will the future architecture have a similar design concept of SD-WAN, including the separation to include an authenticator manager for the configuration and a route reflector similar to BGP or OMP?
I would love to understand BGP well enough to give you an intelligent answer. What I would say is that the mechanisms that we're contemplating for interregional forwarding at this point are, if you look at them from 5,000 feet, they look BGP-like. The regions look autonomous region-ish, but in detail, they are different. There are things that work terrific for BGP and the internet that are ultimately not delay tolerant. And so there are inevitably going to be some design elements of interregional forwarding that will be different from the way BGP works. We certainly want to be able to take inspiration from the very successful architectural functionality that is built into the internet. Some of it we can just use, and some of it we will just have to be inspired by.
Okay, another question from Quadri Adebawale. Also, I've been trying to understand more about ION. I would like to know if the software handles a broadcast message being handled when it occurs.
I'm not absolutely sure I understand the question, but let me answer a question that I think I understand, which is a couple of questions. One is that there is a prototype neighbor discovery mechanism that there's an internet draft written for like a long time ago that is based on IP broadcast, and ION does implement that neighbor discovery protocol. And so in that sense, there are broadcast messages that ION handles and responds to. Those are a low layer of the DTN stack. There are things that enable nodes to establish connectivity between them. Broadcast within the BP-based network is not defined anywhere. And as far as I know, it's not implemented anywhere. What is implemented, at least in ION, is a multicast capability. There's a prototype implementation that leverages off contact graph routing to enable sort of ad hoc, just-in-time construction of functionally a multicast distribution tree that enables distribution of multicast messages through the network in an efficient way, rather than just sending a separate unicast message to every member of the multicast group. That capability has been in ION for a long time and works really well. It's nowhere near being standardized. The DTN working group, IETF, has got a new charter now that they've published 4 standards check RFCs on DTN. And that new charter, I think, ultimately will include the beginnings of looking at the multicast capability, but it's really very far from standardization at this point.
Okay. And a question from Christopher Lowe. Assuming we do have widespread adoption of multi-stakeholder missions participating in a single SSI, how big a part do you think economics and politics will play in terms of resource sharing and information relay, etc.?
Well,
no part at all.
Sorry, not at all. Yeah. Everyone will be wholly disinterested the whole time. No, clearly it will. And there isn't anything special about the solar system internet in this regard. There will be political negotiations and business negotiations that will have to occur in order to make any of this stuff work. The details of all that are things that will, I think, naturally evolve as we establish some standard mechanisms for moderating the cross support among agencies and among agencies and commercial entities eventually. G is certainly not trying to dictate that, and maybe not even speculate on it. I think our safest course there is to wait and see what else.
And finally, a couple of comments from Vint. Tough part will indeed be how to allow autonomous administrative control of assets that may be used as transit nodes in a multi-region system.
Yeah, it's the operators of these assets going to have to be responsible and autonomously operate the assets, but do so in a way that complies with service agreements that they've established with other agencies. That is certainly not the world's easiest thing, but I think it's a doable thing. In the internet, different internet operators carry each other's traffic. There are ways to make that work. I think it's possible, but certainly not trivial.
Okay. And one final comment from Vint. Route reflector is not likely. The basic mechanism for forwarding will be multiple contact graphs.
I'm happy to agree with that because I don't understand what route reflectors are. I should understand that better, but I don't. So I will defer to Vince's expertise on that one.
Okay. That seems to be about the concluding questions for our Q&A session. Thanks, everyone, for attending. I think this has been really informative and generated some good discussion. Just want to remind you that we do have quite a few of these IPNSIG Academy events planned once per month. Next month, I believe, is Dr. Laura Suzuki doing some software demos. And if you have any questions, please drop a line to secretariat@IPNSIG. Here's the schedule. And I did remember correctly. And as we nail down the speaker dates, we'll be updating the table on the website with those dates. And become a member. Actually, as of this morning, we were up to 878 global members. So that continues to grow at a fairly healthy pace. And it's very easy. Just drop us a line at membership@ipnsig.org. We have had some issues with ISOC's membership software portal, and we've had some discussions with their IT people. But for now, if you drop us a line at ipnsig.org, we can manually add you to the database. So thanks very much, everybody. I hope you enjoyed it and found it informative.
Thanks, everyone.